Welcome back, everyone. Ready for another deep dive?
Always.
Well, today we're taking a look at Roentgenium.
Oh, interesting choice.
Yeah, I figured we could go back to the periodic table for this one, see what's new.
I like it.
So, Roentgenium, element 111, not exactly a household name.
Definitely not something you run into every day.
Named after, Wilhelm Röntgen, of course.
X-ray pioneer.
Exactly. And this element is every bit as intriguing as its namesake. For one thing, it's synthetic.
Ah, so not something we just dig up out of the ground.
Nope. Gotta make this one ourselves in a lab. And it's also intensely radioactive.
Sounds a little dangerous.
It can be. And the half-life of Roentgenium, well, let's just say it's not hanging around for very long. We're talking seconds.
Seconds. Wow, that's fast.
Super fast. Yet, despite its fleeting existence, scientists believe it could share some remarkable similarities with gold.
Now that's a head-scratcher. Super unstable, but maybe kind of like gold.
Okay, I'm intrigued. So how in the world did we even discover something that disappears practically the instant it's made? Yeah, that's a great question. The journey to Roentgenium, well, it had a few bumps in the road, you could say.
I'm guessing it wasn't just mixing a couple things in a beaker.
Definitely not. Back in 1986, they actually tried to synthesize it at the Joint Institute for Nuclear Research over in Dubna, Russia.
Ambitious. So what happened?
Well, the thing about creating super heavy elements like Roentgenium is it's tricky business. You're basically smashing atomic nuclei together.
Try to force them to fuse. I can imagine that's not easy.
You've got it. And nuclei, well, they've got a natural repulsion to each other.
Right, so you need immense force to overcome that.
Exactly. So while they did produce some promising nuclei, it wasn't quite enough to definitively claim a discovery. Close, but no cigar.
Oh, so close. But science demands that certainty.
Absolutely. But the story doesn't end there. A few years later, in 1994, a team led by Sigurd Hoffmann at the GSI Helmholtz Center for Heavy Ion Research in Germany, they picked up where that first attempt left off.
All right, so round two, what did they do differently?
They decided to bombard bismuth with nickel nuclei.
Okay, I'm no nuclear physicist, but that sounds pretty intense.
It is. It's like science fiction levels of intensity. But you know what? It worked. They actually managed to create 3 atoms of Roentgenium.
Wait, 3 atoms? That's it?
That's all it took to rewrite the periodic table.
I guess every atom counts when you're dealing with something that rare. But 3 atoms? How can you even be sure?
Well, naturally, a claim this groundbreaking needed some serious checking.
Yeah.
So the IUPAC Joint Working Party, they scrutinized all the evidence.
The scientific peer review process in action.
Yep. And after a very thorough review, they confirmed it. GSI's experiment, it went down in history as the first successful synthesis of Roentgenium.
Officially in the periodic table. But to be extra sure, I'm guessing they didn't just stop there.
Oh, you know scientists. They're all about that reproducibility. So in 2002, GSI, they did the whole experiment again. And guess what?
They got 3 more atoms.
Bingo! 3 more atoms, confirming their original findings.
Talk about attention to detail. Okay, so we've established Roentgenium exists, it's super rare, and insanely radioactive. But I've got to ask, what does all that radioactivity actually mean in practical terms? Like, if we could see a chunk of Roentgenium, what would happen?
Good question. It all comes down to that crazy short half-life.
Right, we're talking seconds, not years.
Exactly. Think of it this way. Imagine a fresh-baked cookie, right? Over time, what happens? It crumbles. Eventually, it's gone.
Sad but true.
Radioactive elements, it's like that cookie, but on an atomic scale. They decay and transform into other elements over time. And a half-life, that's just the time it takes for half of the sample to go through that decay process.
Okay, that makes sense. But most stable elements, their half-lives are, well, pretty long.
Billions of years, some of them.
But not our friend Roentgenium.
Nope. The most stable isotope we know of, Roentgenium-282, it's got a half-life of, wait for it, just 100 seconds.
Just like that. Poof, pretty much. It's why studying this element is a race against time. So how do you even study something that's basically disappearing as you look at it?
Well, it's definitely a challenge.
I bet. Do we even know what it looks like?
We can make some educated guesses based on where it sits on the periodic table. Scientists believe it's probably a solid at room temperature, and maybe a silvery white color like its lighter cousins.
Cousins, who are we talking about?
Copper, silver, and gold.
Oh, right. They're all in the same group, right? Group 11.
You got it. So even though we can't really, hold a piece of Roentgenium in our hand and examine it.
Because it would vanish before we could blink.
Right. But we can still learn about it. Scientists have even predicted its second ionization energy.
Hold on. Remind me what that is again.
Basically, it's the amount of energy you need to rip an electron away from a Roentgenium ion.
Ah, got it. So what's the prediction?
It's supposed to be pretty similar to silver's.
Hmm, interesting. So we've got this super unstable, super rare element, but it might share some properties with silver. Okay, I'm following so far. But earlier, you mentioned that Roentgenium could be similar to gold. How is that even possible? They're so far apart in the periodic table.
That's where things get really fascinating, because despite being distant relatives, they're predicted to have some pretty striking similarities in their chemistry.
Hold on. Chemistry. But we're talking about something that barely exists for more than a minute. How can you even begin to figure out its chemistry?
That's what we're going to dive into next.
It all comes down to Roentgenium's place in the periodic table. Remember, it's in group 11, just like copper, silver, and gold.
Right, right. They're all in the same family, but Roentgenium, well, it's kind of the mysterious distant cousin, right?
Exactly. And you know what's really cool? Scientists predict that Roentgenium might have stable +5 and +3 oxidation states.
Okay, break that down for me. What does that even mean?
So oxidation states, they basically tell you how an element likes to gain or lose electrons when it forms chemical bonds.
Ah, okay. So it's about how it interacts with other elements.
You got it. And here's the thing. Those +5 and +3 states, they're not something we usually see with copper, silver, or gold.
So Roentgenium's got some unique moves up its sleeve.
You could say that. And it's all thanks to something called relativistic effects.
Relativistic effects. Okay, now you're just messing with me, right?
I promise, it's a real thing.
Yeah.
Basically, when you've got electrons zipping around a nucleus as heavy as Roentgenium.
Massive, right? 111 protons.
Exactly. Well, those electrons start to approach the speed of light.
Whoa.
Yeah.
Well,
And that's when things get weird. Einstein's theory of relativity, it starts to kick in. It actually affects the way those electrons behave and ultimately how Roentgenium interacts with other elements.
wow, so we're talking serious physics here.
It's all connected.
Yeah.
Relativity, chemistry, the periodic table. It's amazing.
It's mind-blowing to think that we can understand these things, even for an element that exists for just a few fleeting moments. But I gotta ask, what's the point? I mean, why do we even care about Roentgenium? It's not like we're gonna be making, Roentgenium rings or anything.
That's a question that a lot of people ask, and it's a valid one. But for scientists, it's not just about practical applications. It's about pushing the boundaries of knowledge. The periodic table is like a map of the universe. And by exploring the edges of it, by studying elements like Roentgenium, we're essentially expanding that map.
We're explorers charting unknown territory.
Exactly. And who knows what we might find? I mean, there's this whole concept of the island of stability, this hypothetical region on the periodic table where super heavy elements, well, they might actually be stable.
Remind me about that island of stability thing again.
Right. So we've talked about how most super heavy elements are, well, incredibly unstable. They decay in fractions of a second. But the island of stability, it's this idea that maybe, just maybe, there's a special combination of protons and neutrons that could lead to super heavy elements that are much, much more stable.
Instead of, vanishing before we can even blink.
Exactly. We're talking years, centuries, maybe even millennia.
No, that would be incredible. But why do we think this island of stability might even exist?
It have to do with the way protons and neutrons arrange themselves inside the nucleus.
Right, like they have these specific energy levels.
You got it. And there are theories that certain magic numbers of protons and neutrons could lead to extra stable configurations. Kind of like, well, imagine a perfectly stacked Jenga tower.
Okay, I'm picturing it. So these magic numbers would make the nucleus extra strong.
Exactly. And that extra stability, well, it could mean a much longer lifespan for those super heavy elements.
So it's a numbers game, finding the right combination to unlock this island.
Pretty much. It's a huge challenge, though, both theoretically and experimentally.
Yeah, I bet. But if we did manage to find those magic numbers, what could it mean?
The implications would be huge. I mean, think about it. If we could create super heavy elements that were actually stable, well, it would revolutionize our understanding of nuclear physics.
And maybe even lead to some crazy new technologies.
Who knows what's possible? But even if we never reach this fabled island of stability, even studying elements like Roentgenium, it's helping us understand the fundamental building blocks of matter in ways we never could before.
It's pushing the limits of science.
Absolutely. And who knows what amazing discoveries are waiting for us on the horizon. Every new element we synthesize, every experiment we conduct, It's a step further into the unknown.
It really makes you appreciate the ingenuity and the dedication of the scientists working on this stuff.
Absolutely. They're the pioneers pushing the boundaries of what's possible.
Speaking of pushing boundaries, maybe it's time to wrap up our deep dive into the incredible world of Roentgenium. What are your final thoughts on this mind-blowing element? It's been quite the journey, hasn't it? Roentgenium. I mean, who knew an element could be so elusive and so
I
fascinating?
know, right? It's like it exists, but it doesn't.
Yeah,
At least not for very long.
exactly. And yet, we can still learn so much from it. It really shows you how far science has come.
And how much more there is to discover.
Absolutely. So, to wrap things up, I want to leave our listeners with a thought. Imagine just for a second that we could somehow make Roentgenium stable.
Stable. You mean like it wouldn't decay in seconds?
Yeah. What if we could actually hold a piece of it in our hands? What would that mean?
Wow, okay. That's a really interesting question. I mean,
Uh,
first of all, we'd have to figure out how to make enough of it to actually study.
Right. No more three-atom experiments.
Exactly. And then we'd have to see if it really does behave like we predict.
Yeah.
Would it really have those unique oxidation states? Would it really be similar to gold in some ways?
It would open up a whole new world of possibilities.
And who knows what kind of technologies could come out of that? Stable Roentgenium? I mean, it could be revolutionary.
It really makes you wonder, doesn't it? What other secrets are hiding out there in the universe just waiting to be discovered?
That's the beauty of science. It's all about exploring the unknown.
Well said. And that brings us to the end of our deep dive into the world of Roentgenium. I hope you all enjoyed the journey as much as we did.
It was a blast.
Thanks for listening, everyone, and until next time, stay curious.